Okay, so suppose that we have some type of bowl like this. Something like that, right? And in that bowl, we have a bunch of poker chips that are all labeled with a number. We'll say that the labels will go from 1 through 9, and we'll throw a 0 in there. Why not? Okay? So, what we're going to do is we're going to define two events. The event E is going to be choosing a number less than or equal to 2. I'm gonna flop this here. Maybe write that. And the event F is going to be choosing a number greater than 7. We often utilize Venn diagrams in order to show events in a sample space. What does that look like? Well, usually we just make a big rectangle that represents our full sample space, often labeled S, and then we draw circles to represent the events. If these events have outcomes that are similar, we usually overlap them. If they don't, we keep them separate. It appears that looking at these events of a number less than or equal to or a number greater than 7, there's no overlap. So what we do is we draw two circles that are separate. So we'll call this the event E and this the event F. According to our events, we should be able to put numbers into the events in the Venn diagram to show what we need. For example, if I say less than or equal to 2, then that means that would be chip 1, chip 2, and chip 0. So we would throw them into E. And for F, greater than 7 does not include 7, so that would just be 8 and 9. We therefore have a bunch of numbers left. So if those numbers don't fall into these events, but they still fall in the sample space, then they would fall within the rectangle, but not the circles. So we're talking about, let's say, 3, 4, 5, 6, and 7. So this would be a great way to display a Venn diagram of our events going on here. The fact that these two events don't share any outcomes, we actually have a terminology for that. We refer to that as disjoint. We'll say disjoint events. Another term for that I see in a lot of other textbooks is mutually exclusive. It's just that this textbook uses the term disjoint more often. All right, let's return to the same bowl of chips. And let's this time define two different events. We'll call again E and F. So let's say choosing an odd number is E. And F is choosing a number that is at most 4. Okay, so again, what we need to do is we need to create a Venn diagram. Okay, again, that'll be the sample space. So if we say at most 4 and choosing an odd number, that there is actually overlap this time between the two events. So that means we would need to draw overlapping circles. Okay, we'll call this E and this F. So let's figure out the events that go in each of these. Well, we know that an odd number would be, let's throw it over here so we have it. So this is going to be 1, 3, 5, 7, 9. And at most 4 is going to be 4 or less. 0, 1, 2, 3, 4. So we need to go in to see which ones overlap. So in other words, which one of these are odd? Well, looks like 1 and 3 are the only places that these two sets overlap. So we start there. We take 1 and 3 and we put it in the overlap. For an odd number, which is E, we need to put the rest of the numbers, 5, 7, 9. And for F, we need to put the rest of those numbers, which are 0, 2, and 4. And then the remaining numbers, which I believe is only 6 and 8, go outside the events, but still inside the sample space. The key here now is, since we do have outcomes in common between the events E and F, we call them joint events or not mutually exclusive events. As you can see from the title of the section, the focus is going to be on something called the addition rule. The addition rule actually tells us the probability of two events occurring, one or the other. So, for example, the probability of E or F occurring is going to always be equal to the sum of the two individual events occurring. But this only occurs if the events are disjoint. Okay, so what does that mean for us? Well, if we go up to our first example, and we were asked to find the probability of choosing a number less than or equal to 2 or choosing a number greater than 7, then this is what we'd be looking for. And since we have disjoint events, we could simply just add the probability of each individual event in order to get our result. So let's do it over here. So the probability of E or F must be equal to the probability of E plus the probability of F, because of the fact that we have disjoint events. So therefore, let's find those probabilities. So first of all, how many chips in the bowl? We have numbered 0 through 9, so that means there are 10 chips, which means the probability of choosing a number less than or equal to 2 would be the 3 outcomes out of the 10 chips. Whereas finding the probability of choosing a number greater than 7 would be the 2 outcomes out of the 10 chips, which would give us 5/10 or 0.5. So therefore, the probability of reaching in that bowl and choosing either a number less than or equal to 2 or a number greater than 7 means that it's going to be one of these 5 numbers, which is 5 out of the 10 total. But here's when it gets tricky. Things can go very wrong for you if you try to use this formula when the events are joint. So for example, this guy down here, this example. Why is that? Well, if you look very closely at the outcomes for these scenarios here, there are 5 outcomes out of 10 that fall in E, and 5 outcomes out of 10 that fall in F. So that would imply that you would do 5 out of 10 plus 5 out of 10, which is all of the outcomes. The thing is, we already know that there are 2 that don't go in those events, which means that is incorrect. So there must be a different way in order to accomplish this. It turns out there very much is. So if you were to use the addition rule of events for joint events specifically, then you would be using this formula instead. Probability of E plus F stays put, but when you're done adding them all together, the probabilities, you also have to subtract the probability of E and F occurring at the same time. My hope is that the formula makes some sense to students already. Again, if you're looking at the outcomes, we're adding them together, we're going to get 10 total outcomes. The problem is that we're actually putting in the outcomes 1 and 3 twice into our Venn diagram. So again, highlighting here, this 1 and 3 not only belong in this event, but also in this one. So those two outcomes are actually the probability of E and F. They make up the probability of E and F. So what do we need to do? We need to remove one set of overlap so that we don't have a doubling up of those outcomes in the middle. Okay, so what does that look like in terms of the formula? Over here, I already wrote out the formula that we had down here. So what are we actually going to do? So again, the probability of E is choosing an odd number. We already know that there are 5 outcomes out of 10 in which that occurs. The probability of F down here is also going to be 5 outcomes because it's the number that is at most 4. So as mentioned, that is going to put us at 10 out of 10, which would imply that that's all the outcomes. We know that is not true. We have 2 outcomes that are not there. So what does that mean for this? This right here represents the probability of the overlap occurring. Here we have 2 outcomes in the overlap out of 10. So therefore we need to subtract that out and we will get 8/10 or 0.8 as our probability. Okay, so the focus basically lies in our 2 formulas for the addition rule. Remember, the key is when you see the word or combining 2 separate events, then that's where the addition rule takes place. You want to determine whether the events are disjoint or joint before using said formula because that will determine which one to use. I also want to make one small point before getting to more examples. When you look at these formulas right here, beware that they are actually quite similar. I mean, if you look here, they're identical. It's just this extra part that's the key. So you can be really logical here and say, well, what if a set of events like the ones up here don't have an overlap? Well, what is the probability of an overlap that doesn't exist? Well, if there's no outcomes there, then that means the probability is 0. And if this is 0, what happens to it? It goes away and you're left with just the original rule. This is a very clear observation to make, and hopefully you can see that the formulas are very much related. All right, let's do a few more examples to make sure things are understood here. So suppose you roll a balanced 6-sided die, find the probability of, well, letter A, rolling a 2 or a 5. Okay, so right away, hopefully everybody notices that the keyword or has been a part of our problem, which means as soon as you see that, your brain is going to go to the addition rule. Second step, we want to determine whether the 2 events listed, so we'll call this, let's use different letters, we'll call this A and B. So the event A is selecting a 2, or rolling a 2, and event B is rolling a 5. We want to determine if these events are disjoint or joint. So all you have to do is ask yourself, can we roll a 2 and a 5 at the same time? That is absolutely impossible. It can either be one or the other, or any of the other outcomes on a dice, but not at the same time. So that means that these are absolutely disjoint events. So next step, you would go to your formula sheet. You would say, okay, well, probability of A or B in disjoint events is going to be equal to the simple addition for the probability of each event. Well, If we have a 6-sided die, that means our sample space is simply 1, 2, 3, 4, 5, or 6. That's all you can actually roll. So out of those 6 options, how many of them are a 2? Well, 1. That's probability of A. Well, what about B? Out of the 6 options, how many are a 5? Well, 1. So that means we get 2 out of 6, which is basically reduces to 1/3 and simplifies to about 0.3 repeating. And that would be our probability. Okay, what about rolling a number less than 4 or an even number? Let's just create variables. It really doesn't matter what they are. Let's say L for less than 4 will be event less than 4, and E will be an even number. Makes sense to me. So the question is, if you're looking at these outcomes, is there an overlap? For example, are there even numbers that are less than 4? I think most of you will look at that and say, absolutely there are, which means that this is an example of joint events, L and E. So therefore, we go to our formula sheets, which is for you would be right here while we're doing this, and we would say, well, we got the probability of L or E is going to be equal to the individual probability sums of L and E, but we have to subtract the probability of their overlap, L and E. Let's look at the probabilities. Well, if we have numbers that are less than 4, what does that pertain to? Well, if we're looking at these values up here, then the ones less than 4 are 1, 2, and 3. That means strictly less than. So there are 3 outcomes out of the 6 that are in L. What about even? Well, that's pretty straightforward as well. 2, 4, and 6 are the only even numbers you can roll on a single die. Again, there are 3 of them. But then we need to subtract the overlap of these two. If you look at these, where do they occur at the same time? Only at one number. So therefore, we can only subtract 1 out of the 6 to get 5/6 as the result. This would be rounded, and it would be approximately 0.83 as our result. Okay, yet another example that we can deal with here. It says, suppose you flip a coin 3 times. Find the probability that the first quarter comes up heads or the same result occurs on all 3 flips. Again, you can see right here we have the term or. So the or allows us to determine that we will be using the addition rule here. But this is a slightly more advanced problem, only because it returns to something that we've seen before that requires development of a sample space. So at the beginning of this, it says you flip a coin 3 times. So we're looking for outcomes of flipping a coin 3 times. So let's list those, our sample space. We've done it before with a tree diagram, so let's try it without. So let's start with a scenario where we have all 3 heads. Now let's move to a scenario where there are only 2. So let's list out 2 heads in the beginning, 2 heads at the end, and staggering heads with the tail in the middle. If you look at those 3, there's no other way that you can get 2 heads in flipping 3 coins. Moving forward, what if we want only 1 head? Well, that means the head can only appear in the 3 spots that you have. That's it, those 3 spots. And finally, no heads means all tails, and we get this. If you recall, that meant that there were 8 possible outcomes. So that sounds like a good denominator for some of the things that we're going to do. So why don't we give a label to these events? Let's say we'll call, it says first result comes up heads. Maybe we'll just call that F for first. And the same result on all 3 flips. Doesn't really matter what it is. We'll just pick, since there's nothing really jumping out at me, we'll just pick, let's say, an M. Okay. So let's say we're looking to find the probability of F or M. Okay, so we have to determine first whether these are disjoint or joint events. My question is, for any of the results in event M where the same result occurs on all three flips, do any of them have a first value of heads? And if you think about that right away, of course they do. Specifically, there's one that does, which means these are joint events with an outcome in common, which means we need to use the larger addition rule, which is going to give us, let me fix that middle M because I was going to write the wrong thing for a second there. M. Okay. So probability of F. So we have to determine that when the first quarter comes up heads. So if you look at our outcomes that we have here, I'll throw a yellow highlight in there. This is first heads, this is first heads, this is, and this is. All the others are first tails, which means when I look at this, I know that there are 4 out of the 8 that come up heads first. What about, I'll use blue for the other one, highlighter. So what if I want to know the same result on all the flips? Well, we know that that occurs in only 2 of the outcomes. That is one of the easier questions to ask. So 2 out of the 8. So therefore, the only thing we have left is to remove the overlap. In other words, is there a scenario in which it occurs that not only is the first quarter heads, but the same result as in all flips? And you can see that that's only going to occur in the one that has both highlighters on it, and that's going to be 1. So that means there's only one event, triple heads, in which that occurs. If you do, you'll get 6 out of 8 minus 1 out of 8, which gives you 5/8 as your result for our probability, which is going to give us exactly 0.6250 as our probability. Okay, I do want to talk about one more concept here, and you'll see that I have a graphic display of a deck of cards. So I am aware that not everybody is familiar with playing cards. They might know what they are, but they don't really know the suits or what's on the cards in terms of numbers or letters, whatever it is. So they are so good for showing probability, which means I do some examples using them to help students understand, but I won't be putting them on exams. I'll find another unique way to do so in terms of questions that are in a similar genre. But for now, I do want to talk a little bit about the cards themselves so everybody understands what they're about. Just know that there are 4 suits that you can have. Each row represents a suit here. We have clubs. Let me actually erase this for a second. We have spades. We have hearts. We have diamonds. Okay, I'm just going to move over a little bit. So right here, we got the 4 suits. Okay, there are 13 cards in each suit for a total of 52 cards in the deck. If you look closely, these right here are called face cards because they're the only ones with faces on them. They are the king, queen, and jack. You also could look at this and be like, okay, so what about which numbers are even? You could say, well, 2, 4, 6, 8, and 10 are even because those are actual even numbers. You could, just one thing about the ace is not considered a number, nor is it considered, let's say, a high or a low card. You think of it as just sort of a special card in the deck. So, and it's definitely not a face card, so be careful with that. But we're going to run through questions here that I just want you to get a general idea of what's going on in the deck. As I said, it's not going to be on exams, but it actually is pretty useful for teaching probability. Okay, so let's just do 2 quick examples, and I'll keep that graphic at the top of what we're doing here. So what if we have the 52 playing cards, and we wanted to determine the probability of getting a face card or an ace? So again, let me just highlight this guy right here. We have the OR word, which means we have the addition rule. So if we're determining a face card or an ace, I've already mentioned that aces are not face cards, which means that we have our aces over here, and we have our face cards over there, which means there is no overlap between them. So that means if we call, let's say, this the F for face card and this A for ace, then the probability of F or A, which is what they're asking for, is going to be equal to the simple addition of the two events because they are disjoint. So how do we play with this in terms of cards? Well, we want to find the probability of a face card. Well, out of 52 cards, how many of them are face cards? So what we want to do is we want to count how many are here. Well, we have 4 suits by 3 face cards per suit, gives us 12 total cards to deal with. And we have, for the ace, the probability of ace, we also have 52 total cards in our sample space. And we only have 4 aces, which means we're going to get 16 out of 52 as our resulting probability. And that is going to be approximately 0.3077. Okay, so, and lastly here, it says probability that we select an even numbered card or a club. So again, there's your or right there. We can jump right into it. We can name this, let's say, E for even and C for club. So we're looking for the probability of E or C. The question is, are there any even numbered clubs? Clearly there are. There's a lot of clubs, odd and even, so that means this is going to be a joint set of events. We need the bigger rule, so probability or bigger addition rule. So we're going to take the sum of the two events, but then we're going to have to subtract out the overlap of them. So let's get on that. So we have our even cards. So let's count them. We got 1, 2, 3, 4, 5 with even numbers on them. But we also have 4 suits. So 5 times 4 is going to give us 20 even cards out of our 52 in our deck. For our clubs, we already mentioned that there are 13 in each suit. So 13. But now we're going to have to take out how many out of 52 is there an overlap. So what does that mean? That means we're looking for the even number clubs. Well, we already highlight them with stars here, how many even number clubs are. There are 5 in each suit, and we're looking for specifically clubs, so we're taking out 5. So if we do 20 plus 13 minus 5, we're going to get 28 out of 52, which is going to give us approximately 0.5385 as our probability.